This is Dr. E. Helena, working as an assistant professor in the Department of Mathematics, Fatima College, Madurai. I am happy to share my lecture on the topic self-adjoint operators on Hilbert space. In this lecture, let me introduce self-adjoint operator and few of its properties. Definition of self-adjoint operator. An operator T on a Hilbert space H is said to be self-adjoint if T star is equal to T, that is conjugate of T is equal to T. From the definition we have the following properties. 0 and I are self-adjoint operators. The next one, an operator T on H is self-adjoint, then inner product of Tx, y is equal to inner product x, ty for every x, y belongs to H and conversely. Let us now prove this property. For that, let me assume T to be self-adjoint. What we have to prove here is inner product Tx, y is equal to inner product x, ty. So by the definition of T star, the adjoint operator, we have inner product Tx, y is equal to inner product x, T star y. As T is self-adjoint, we know T is equal to T star. So replacing T star by T, we get inner product Tx, y is equal to inner product x, ty. This is what we have to prove. To prove the converse, let us assume that inner product Tx, y is equal to inner product x, ty for every x, y belongs to H. Here we have to prove T is self-adjoint. That is to prove T is equal to T star. Again, as T star is the adjoint operator, by the definition we know inner product X, y is equal to inner product x, T star of y. By assumption, we have Tx, y is equal to inner product x, ty. Therefore, x, ty is equal to x, T star y. So, which implies inner product x, T star T minus T star of y is equal to 0. As x is not equal to 0, we have T minus T star y is equal to 0 for all y belongs to H. Hence, T is equal to T star. Third property, for any T belongs to beta of H, we have T plus T star and T star T are self-adjoint. That is T plus T star the whole star is equal to T plus T star and T star T the whole star is equal to T star T. So let us first consider T plus T star the whole star. So applying the rule, we have T star plus T double star. Also we know T double star is equal to T. Thus we have T plus T star the whole star is equal to T star plus T. Thus T plus T star becomes a self-adjoint. Next let us consider T star T the whole star, which is equal to T star T double star, because we know T1 T2 the whole star is equal to T2 star T1 star. Also we know T double star is equal to T. Therefore we get T star T the whole star is equal to T star T. Thus T star T is self-adjoint. Next theorem. If An is a sequence of self-adjoint operators on a Hilbert space H, and if sequence An converges to an operator A, then A is self-adjoint. So let us consider sequence of self-adjoint operators on a Hilbert space H as sequence An. Also we have sequence An converges to an operator A. What we have to prove here is A is self-adjoint. That is to prove A is equal to A star. So let us consider sequence An be a sequence of self-adjoint operators on a Hilbert space H and An converges to A. As this is a sequence of self-adjoint operators, each An is self-adjoint, that is An star is equal to An for all n. We have to prove A is self-adjoint. So for that, let us consider A minus A star. Here let me add and subtract An as well as An star, so that A minus A star becomes A minus An plus An minus an star plus an star minus a star. Considering norm for individual terms, we have norm a minus a star less than or equal to norm a minus an plus norm an minus an star plus norm an star minus a star. Here the second term we have norm an minus an star. We know an is self-adjoint. Therefore an star can be written as an. Also we know an star minus a star as an minus a the whole star. Therefore we have norm a minus a star less than or equal to first term. Let me take minus outside so that first term becomes minus an minus a plus second term becomes an minus an as an star is equal to an, and the third term an minus a the whole star as norm an minus a, which implies norm a minus a star less than or equal to first term becomes norm an minus a, second terms becomes 0, and the third term is norm an minus a, which is equal to twice norm an minus a. As an converges to a, this term converges to 0 as n tends to infinity. Therefore, we have norm a minus a star is equal to 0, which implies a is equal to a star. Thus, we have proved a is self-adjoint. Next theorem. Let S be the set of all self-adjoint operators in beta of H. Then S is a closed linear subspace of beta of H, and therefore S is a real Banach space containing the identity transformation. Here let us assume the self-adjoint operators as the collection S. What we have to prove here is S is closed linear subspace of beta of H. As we know, beta of H is complete. If we prove S is closed linear subspace, the closed subspace of a complete space becomes complete. Hence, S becomes a Banach space. By the property of self-adjoint operator, we know 0 is self-adjoint. Therefore, the set S which contains the self-adjoint operators is non-empty. First, let us prove S is a linear subspace. For that, let us consider A1, A2 belongs to S. What we have to prove here is alpha A1 plus beta A2 belongs to S, where alpha, beta are real constants. Since we are assuming A1, A2 in S, we have A1 star is equal to A1 and A2 star is equal to A2. Let us now consider alpha A1 plus beta A2 the whole star, because we have to prove alpha A1 plus beta A2 belongs to S. That is, alpha A1 plus beta A2 is self-adjoint. To prove self-adjoint, we have to prove alpha A1 plus beta A2 the whole star is equal to alpha A1 plus beta A2. So, we are considering alpha A1 plus beta A2 the whole star. So, we know T1 plus T2 the whole star is equal to T1 star plus T2 star. So, alpha A1 plus beta A2 the whole star can be written as alpha A1 the whole star plus beta A2 the whole star. Also, we know that alpha A1 the whole star is equal to alpha conjugate A1 star. So, we have alpha A1 star is equal to alpha conjugate A1 star and beta A2 the whole star as beta conjugate A2 star. As alpha and beta are real constants, alpha conjugate and beta conjugate is nothing but alpha and beta. Since A1 and A2 are self-adjoint, A1 star and A2 star can be written as A1 as well as A2. Therefore, alpha A1 plus beta A2 the whole star becomes alpha A1 plus beta A2, which implies alpha A1 plus beta A2 belongs to S. Thus, S is a real linear subspace of H. So, now it is enough to prove S is a closed subspace. To prove S is closed, let us consider a limit point of S, and we will prove that this limit points belongs to S, so that S becomes closed. So, let A be any limit point of S. A is a limit point of S. Therefore, there exists a sequence of operators an in S such that an converges to A. What we have to prove here is A belongs to S. That is A is self-adjoint. That is to prove A is equal to A star. So, for that let us consider norm A minus A star. We will add and subtract by an. So, we have norm A minus an plus an minus an star. By the property of norm, this is less than or equal to norm A minus an plus norm an minus A star. Let us now consider the second term, norm an minus A star. We will add and subtract by an star. So that this becomes norm an minus an star plus an star minus A star. Again by the property of norm, this is less than or equal to norm an minus an star plus norm an star minus A star. Therefore, norm A minus A star is less than or equal to norm. Removing minus outside, it becomes an minus A plus norm an minus A star plus an star minus A star. Since an star is equal to an and an star minus A star is equal to an minus A the whole star, and norm an minus A star is equal to norm an minus A, we have norm A minus A star less than or equal to first term in equation 4 as an minus A plus second term is 0 and the third term becomes norm an minus A. Thus we have norm A minus A star less than or equal to twice norm an minus A, which converges to 0 as we know an converges to A. So this implies norm A minus A star is equal to 0, which implies A minus A star is equal to 0. That is A is equal to A star. That is A is self-adjoint. That is A belongs to S. Hence S is a closed linear subspace of a Banach space beta of H. Thus S is a closed linear subspace of a Banach space, and by the property S becomes a real linear subspace. Also we know that by the property of self-adjoint I is equal to I star. That is the identity operator I is equal to I star, which shows that I belongs to S. Hence the theorem is proved. Next theorem, if A1 and A2 are self-adjoint operators on H, then their product A1, A2 is self-adjoint if and only if they commute. So, we will consider two self-adjoint operators, then their product is self-adjoint if and only if they commute. That is A1, A2 is equal to A2, A1. So, let us consider A1, A2 be two self-adjoint operators on H. As A1 and A2 are self-adjoint, by definition we know A1 star is equal to A1 and A2 star is equal to A2. Let us assume A1 and A2 commute. That is A1, A2 is equal to A2, A1. We have to prove A1, A2 is self-adjoint. That is to prove A1, A2 the whole star is equal to A1, A2. So for that let us consider A1, A2 the whole star. By definition this becomes A2 star, A1 star. As A1 and A2 are self-adjoint, A2 star can be written as A2, A1 star can be written as A1. As by the hypothesis A1, A2 commute, A2, A1 can be written as A1, A2. Thus we have A1, A2 the whole star is equal to A1, A2. That is A1, A2 is self-adjoint. To prove the converse, let us assume that A1 and A2 be two self-adjoint operators. With the assumption A1, A2 is self-adjoint, we have to prove A1 and A2 commute. Since A1, A2 is self-adjoint, we have A1, A2 whole closure star is equal to A1, A2. So by definition A1, A2 star is equal to A2 star, A1, A1 star. Since A1 and A2 are self-adjoint, A2 star is written as A2, A1 star is written as A1. Therefore, we have A1, A2. By hypothesis, A1, A2 the whole star as A1, A2 and here we have a1 a2 the whole star as a2 a1. Therefore a1 and a2 commute. Next theorem, if T is an operator on a Hilbert space H, then T equal to 0 if and only if inner product Tx comma y is equal to 0 for all x comma y belongs to H. That is, this is the condition of a zero operator, necessary and sufficient condition for an operator to be an zero operator. So let us consider T to be a zero operator on H. Then for all x comma y belongs to H, we have inner product T x comma y is equal to, as T is a zero operator, it can be written as inner product 0x comma y, which is equal to 0. Thus we have proved inner product Tx comma y is equal to 0 when T is a zero operator. Conversely, let inner product Tx comma y is equal to 0 for every x comma y belongs to H. Let us take y is equal to Tx. Therefore, we have inner product Tx comma replacing y by Tx. It becomes inner product Tx comma Tx is equal to 0 for all x belongs to H. That is, Tx is equal to 0 for all x belongs to H, which implies T is equal to 0, which is the zero operator of H. Thank you.